Hello, everyone. I hope all of you are doing great. Thanks for joining in today. Um, we've set up this webinar between Shemco and Carus, which is the largest manufacturer of potassium permanganate in the world, to talk about the application of the oxidant sodium or potassium permanganate to remediate recalcitrant compounds. There's some legislation change that have been occurring in Canada all across where manganese has been targeted as a contaminant of concern. So the presentation today is here to discuss and explain a little bit about what are the impacts of using permanganate for water, for soil, from the air. We'll be hearing from John Ball, which is one of the technical specialists within Carus, that will do the lecturing today. He will go on with his presentation. You will see at the bottom there's a chat button, so you could use this to ask your question, and we'll cover any question you have at the end. So with that, I will leave the floor to John. Thanks for attending today, and hope it will be a great experience for you. Thanks again. Have a good one.
All right, thanks, Sean, very much for that introduction, and welcome to everybody. Good morning or good afternoon, depending on where you're located. We do have a very nice presentation for you today on manganese in the environment. And as John was saying, we're looking at how the new Canadian water quality and drinking water guidelines regarding manganese may impact the use of permanganate products in ISCO soil treatment. So here are the topics that I'm going to cover today. And we've prepared the presentation really to encourage an open discussion about this particular topic. And we've reviewed information on manganese in nature, its chemistry, what is known about the fate of manganese pre and post ISCO treatment. And I would just add that there's quite a significant data gap in this particular area, which would be a very useful follow-on conversation to this presentation. And there's really a very straightforward explanation for that, and that is up to this point, manganese has not really been an element of concern in any of these application areas. So really every day at Carus, we receive a variety of important and interesting questions about the physical and chemical characteristics of our permanganate family of products. And for ISCO treatments, we're focusing specifically on RemOx L and RemOx S ISCO reagents. Now, both of these products are chemically manganese-based. In the technique of in situ chemical oxidation, RemOx reagents are used to oxidize and remove subsurface chlorinated solvent contamination, typically TCE or PCE. With this treatment, manganese is certainly introduced into the soil of the target treatment zone by the subsurface injection of permanganate. Given the new manganese drinking water and water quality guidelines in Canada, it's important to understand the fate of this manganese in the soil and whether it affects the groundwater in the area. This knowledge will help to inform us regarding best practices for ISCO sites. Now, in preparing this, it seemed to me that there are really three fundamental questions that must be addressed when investigating any link between permanganate ISCO treatment and groundwater that is subject to the new Canadian guidelines for manganese. First, should we expect that a potable water well with no point of use treatment will be located on or near an ISCO treatment site? Secondly, does manganese migrate off the Permanganate ISCO treatment site at concentrations greater than background? Could it impact a surface water supply at greater than 3.6 milligrams per liter as dissolved manganese for 2 or 4 days? And finally, what is the pre-ISCO concentration of naturally occurring manganese at the site, and does it currently migrate down gradient? So in 2019, Health Canada published new guidelines for manganese in drinking water, setting a maximum acceptable concentration, a MAC, of 120 micrograms per liter. In addition, the guidelines were revised and lowered the aesthetic concentration target to 20 micrograms per liter. Aesthetic standards are intended to minimize discoloration, staining, and particulate accumulation in distribution system pipes and storage tanks. Now, just as an aside, I would say that a potable water treatment plant facility, these are not particularly unusual targets, although some waters, they can be difficult targets to meet on occasion. But many systems have been meeting this aesthetic quality standard really for years. These guidelines are now the lowest global standards when compared to the concentrations targeted by other water agencies. The MAC values are based on recent data of potential negative health impacts of long-term ingestion of dissolved manganese in drinking water by the vulnerable populations of infants and children. And of note, the WHO has now followed this lead, and in 2020 proposed new health-based guidelines as well. Also in 2019, the Canadian Council of Ministers of the Environment issued these environmental quality guidelines. Please note that they are specific to dissolved manganese 2 ions, the form of manganese that is bioavailable. Short-term exposure is based on a 48-hour or a 96-hour LC50 for 17 aquatic species. Long-term exposure to manganese 2 ions is based on 14 species of invertebrates, aquatic plants or algae, and fish. The data uses the 10% effect concentration for 10% of exposed species, an EC10. The exposure period was for as little as 7 days or for as long as 65 days for the long-term guideline. So let's look at a little background information on manganese in the environment. What do we know? We know that manganese occurs naturally, and it's the 12th most abundant element in the Earth's crust. Manganese is generally found in the form of stable oxides, carbonates, and silicates in over 100 minerals. Pyrolusite, or manganese dioxide, is the predominant form, and these minerals are immobile, but under certain conditions, these solids can erode or dissolve, leading to the detection of low levels of manganese in water. How about manganese in soil? What do we know there? Well, we first know that we're surrounded by it. In surveys across the US and Canada, manganese concentrations in soil fall into the range of 40 milligrams per kilogram, or parts per million, to 900 milligrams per kilogram. Its presence in soil results in vegetable and animal foods that contain varying amounts of manganese themselves. Manganese is, in fact, classified as an essential nutrient and is added to certain foods and nutritional supplements. And then chemically, what do we expect at an ISCO site based on permanganate chemistry? The intent of the permanganate subsurface injection is to react with and mineralize chlorinated solvents such as trichloroethylene. Under the conditions of the treatment environment, the reaction is shown here. In this reaction, there are several species of manganese that participate. The first is the permanganate ion itself, or manganese in the +7 oxidation state. It is soluble in water and is easily traced because it imparts a distinctive pink to purple color to the water. Also, when permanganate is present, it will be reflected in a highly positive ORP measurement. Some of this data will be presented later in the presentation. Because it dissolves in water, it is mobile in the subsurface. The end product of the reaction is manganese 4, or manganese dioxide solids. The manganese dioxide is immobile and remains trapped in the soils of the target treatment zone. And this has been reported repeatedly in the literature. In fact, in practice, the concern generally is that often rapid and heavy formation of manganese dioxide will lessen the permeability of the formation. Finally, it's important to recognize that the manganese +2 ion. Under acidic reducing conditions, it can be formed when manganese dioxide reacts with materials in the soil. Manganese 2 ion is soluble, and therefore it is mobile. The metals are everywhere in the natural environment and can vary widely in concentration depending on the local geology. Mobilization occurs when the metals associated with the solid phases are released into aqueous solution. And once in solution, the metals will move with the groundwater or with rainwater infiltration. To this point, ISCO treatment sites have broadly studied regulated metals, and these include arsenic, cadmium, chromium, copper, lead, mercury, nickel, selenium, silver, and zinc. Generally, manganese has not been of interest and little data has been collected. So can solid manganese compounds dissolve and move off-site? There has been some work done in this area. In laboratory research conducted by Loomer, the question was investigated by exposing manganese dioxide-coated sand to groundwater containing dissolved organic carbon, a potential reducing agent. This short-term study concluded, 1, manganese release was controlled by a combination of factors. 2, manganese carbonate solids form via precipitation almost immediately after release. And finally, 3, small, less than 0.05 milligram per liter concentrations of manganese were released into the groundwater. In his 2001 textbook on permanganate ISCO, Carus notes that as part of a long-term monitoring program, in ISCO sites, manganese levels were evaluated by West and others following field treatment of TCE. The soluble manganese, that's manganese that they filtered with a 0.45 micron filter, soluble manganese in groundwater, the concentrations were measured over 10 months. And the findings included, before permanganate ISCO treatment, there were already background dissolved manganese levels at the site location, and the manganese ranged from 0.1 to 0.5 milligrams per liter. These concentrations are above the Canadian map. As anticipated, very high levels of manganese, dissolved manganese, are found whenever permanganate is still present in the sample. In this case, values ranged from 90 milligrams per liter to 5,000 milligrams per liter. In monitoring wells where the permanganate had been fully consumed, the dissolved manganese levels dropped to near or slightly above the normal background values. The measured concentrations in this case ranged from 0.03 milligrams per liter to 3 milligrams per liter. From the Department of Defense, the Strategic Environmental Research and Development Program, and the Environmental Security Technology Certification Program, they published a textbook in 2011 that reviewed all ISCO technologies. And in that text, the secondary impacts of ISCO were addressed, including a review of metals data for 23 ISCO sites. 10 of the sites reported no change in metals concentrations above background during and after ISCO treatment. 13 sites saw metals concentrations that were elevated above baseline. The metals that were commonly increased were arsenic, chromium, manganese, and nickel. However, the duration of the increases varies from less than 1 month to greater than 36 months, and were limited to within the ISCO target treatment zone for all but 2 sites. And quoting from the report, the 2 sites with down gradient metals increases were both continuous ozone or peroxone sparge applications. In 2011, in a master's thesis, Kellyanne Moore evaluated ISCO geochemical parameters by reviewing the water quality data for 30 permanganate ISCO sites. Of specific interest was whether there was long-term impacts on the groundwater quality as they related to the site and design conditions. There's a lot of information in this report, and it's very difficult to summarize, but bear with me. The 6-month to 2-year impact on groundwater quality by subsurface oxidation injection was reviewed for 30 sites. And the analysis determined the geochemical parameters returned to pre-ISCO conditions within the time frame that I mentioned, 6 months to 2 years. The impacts were localized to the treatment target zone. Most mobility is found in soils that are permeable and homogeneous. And at most sites, it will take the groundwater more than 1 year to reach 30 meters from the point of injection. Manganese concentrations can be predicted by pre- and post-ISCO oxidation reduction potential, ORPs. However, it's likely that the high ORP post-treatment actually indicated that there was a permanganate residual present. At any ISCO sites, and it is important to understand what the natural manganese background levels are. Some data has been recorded and is included in the thesis that Moore presented. And here are the takeaways. Before treatment, the levels of manganese were recorded for the sites. 20 sites reported manganese data for 5 distance intervals from the target treatment zone, ranging from 3 to 30 meters. 14 of the sites recorded naturally occurring levels of manganese that exceeded the Canadian MAC. That was all pre-ISCO treatment. How about post-ISCO treatment? For the 20 sites that reported manganese data, the post-ISCO results can be categorized really into 5 outcomes. First, there are sites that reported small increases. There were 6 of those. And on the slide, you can see the range of manganese that they published. There are actually 4 sites that reported very large increases immediately post-treatment. There are also 2 sites that report small short-term initial increases, but they don't show any follow-up later, so it's likely these sites eventually return to background levels. There are 4 sites that report small short-term increases, but then measured later and found that they returned to background levels. And there are 4 sites that report decreases or no change to the manganese concentration. It's really a positive outcome that 8 sites showed no adverse impact. However, special focus could have been placed on the 4 sites with very high residual manganese concentrations. And it's quite possible that the mass of permanganate applied at these sites was simply too high to begin with. So when the health guidelines were published in Canada, Health Canada also published a fact sheet that described permanganate ISCO treatment, and it offered guidance on its applicability. And here's what the fact sheet includes in their informative summaries. They address waste and discharges and long-term considerations following remediation work. In the guidance document assessment, dissolved manganese is typically not an issue, but should be monitored. And it does caution, however, the potential for off-site migration of unreacted permanganate. Health Canada also provided their local regulators with suggestions on evaluating risk if manganese levels in drinking water exceeded the MAC. And here's what should be done if the manganese concentration is above the MAC. Marginal short-term exceedances need further evaluation, but exceedances may not require immediate action. Chronic exceedances, slightly above the MAC, likely require that infants should not consume formula prepared from that tap water. And finally, concentrations exceeding 0.3 milligrams per liter pose a risk to the broader population. So this gives you some idea of what concentrations they were focusing on. In light of this information, are there valuable steps that should be considered when designing a ISCO treatment program? And certainly there would be. First, review the design conditions at the site. Is it possible there's an untreated private drinking well down gradient of the ISCO site? It should be checked. Evaluate the permeability of the soil medium. If necessary, provide a protective control barrier down gradient of the injection point. And finally, always optimize the mass of the permanganate injected at the site. So let me conclude by revisiting the 3 fundamental questions that I posed at the beginning of the presentation. Question 1 was, what is the likelihood that an untreated potable water well would be located on or down gradient of an ISCO remediation site? And I believe the answer would be that it's highly unlikely close to the site. And further down gradient, this situation really is controllable. Question 2 would be, how likely is it that soluble manganese, or manganese 2 ions, will migrate off the treatment target zone and be detected in untreated potable water wells at levels greater than 0.12 milligrams per liter? And I would add, could this even be correlated between the ISCO injection site and what's happening down gradient in water wells? The answer is this is potentially possible. It would be dependent on the soil geology, the physical, chemical characteristics of the soil, the combinations of treatment techniques, because sometimes there are many, and of course the treatment levels, and any migration barriers that might be installed at the site. And finally, in question 3, what is the pre-ISCO concentration of manganese at the site, and is it migrating down gradient? And the answer is because manganese is everywhere in the environment. The groundwater at many ISCO sites can exhibit natural manganese concentrations higher than the Canadian MAC before treatment begins. There is little or no data that I could find on down gradient migration. So at this point, we'll close and we'll open up the discussion for questions and answers. Go back to John Perret to see if he has any further comments or any questions there as well.
John, one thing that I'd like to point out, and it is true here for the St. Laurent Basin in Quebec, but we have some natural soil in Canada that are already above the standard for soil in manganese concentration. And so what, and I'll let you start with an answer and I'll complement your thought. What would be your say, or how would you approach, if you have a site which is located, let's say, in a silt or in a clay, which has high manganese content, but you still want to use the manganese there. Any thought on this?
Well, my first thoughts, Sean, are that any permanganate we inject and any manganese that forms in the treatment zone is going to stay there. So it would be a very localized increase to what the background is. And I would suggest that it's not going to pose any change to the environments in that particular area. Would you agree with that or disagree with that?
And then I'll do correlate this situation with stuff that happened in I-70 aquifer, which we find often in Alberta or Ontario. They already have high sodium hydrochloride, and we're talking about injecting, let's say, sodium permanganate or even sodium persulfate there. So one of the issue that we found is that you got to look at the whole mass balance. You start and looking at realistically how much kilogram or how many metric ton of that contaminant are you going to include into your soil. Now, in the case of sodium, we've been able to counter this by using a calcium-based activator. So that was able to diminish the SARVA, the sodium absorption ratio for the site. So typically, even if we were applying or putting in some sodium, we're still able to diminish the sodium absorption ratio. For the manganese, though, it's quite different because it is a metal. And if the legislator is typically scared or concerned about the presence of manganese and its leachability, I think the data that you expressed here today is of great help because it kind of could limit off, the migration and showing that the risk of the manganese being mobilized and impact any down gradient receptors is very little. It's just, can you live or not with the manganese in your soil? And through that, it's a case-by-case thing to be handled with legislator and through a mass balance. So that's really the way I would envision it.
And I would, unfortunately, Jean, there is not a whole lot of data present, right? So that's sort of, it's incumbent on us in a treatment site to do a little bit more monitoring than what we have in the past. And I would certainly suggest that we monitor based on the species of the manganese as well, so we can identify whether it's soluble manganese that is moving off site and that is actually the target of the regulations, or whether it's actually solid manganese that is moving down gradient for maybe a short distance, but but probably not a long distance as well.
Yeah. There was one question that's showing on the panel here, John, that I'd like you. So, potable drinking waters, you know, if you are injecting in, and I'm sure the US, contrary to Canada, you guys are using a lot of groundwater to feed the potable water system of the cities,
Yes.
especially in the Midwest. So, was there any permanganate injected near or into potable water drinking aquifers, you know, that you know of during an ISCO approach?
Not that I know of, unless there was some testing many years ago where they had some type of contamination that they were going to try and remove. So it's possible that they may have found a groundwater system where, say, PCE was present in the groundwater, and they may have tried to inject permanganate at that point to destroy the PCE. But remember, in most of those cases, the groundwater supply will probably be treated, so there would at least be a pressure filter on that system that would remove any of the insoluble manganese particles that would be present in the water and take them out of the water before the water is distributed to the city.
I might add to this answer, John, that you know the potassium permanganate is widely used as a pre-oxidation compound for potable water, and your products that are manufactured by Carus in the US are NSF 60 approved. So the reason we're using the manganese normally as a pre-oxidation step is to try to minimize, especially if you're facing high organic loading in your water coming from leaves or from a river, to prevent the formation of these carcinogenic known compound as alloacetic acid, or that can be constructed when chlorine will react with the organic species. So in these cases, as you've explained, you know, manganese is used as a pre-oxidation prior chlorine being added to the water. And obviously all the manganese removed through filtration, precipitation, and sedimentation process. So there's really, you know, minimal impact to the water based on the manganese, which is directly dosed into the water stream. So for me, it's kind of, it falls into the same line of reasoning that you just explained.
That's right. And remember, as I said at the beginning of the presentation, there are already very tight standards on how much manganese should be present in finished water, and they are getting lower. They were at 50 ppb, and they're now pretty much everywhere people are targeting 20 ppb. So these water plants are working all the time to make sure that the residual manganese levels are at very, very low, very, very low concentrations. I would also add, John, that there's some very good work, some out of Canada as well, that looks at the manganese oxide particles as absorbers of impurities such as other metals, and in particular radium removal is a big use for freshly precipitated manganese oxides. So these oxide particles absorb the radium, and then when they are removed on the filter system in the plant, the radium stays behind with the manganese oxide. So that's also another very popular and successful water treatment program.
So I think that pretty much concludes, you know, the question period, unless any other person or want to come in and add up some stuff. But John, I want to first thank you for putting that presentation together for us. The recording, I'm sure Ashley and the Carus team will make it available through your website, and we'll share the link to those people that could not attend with us today. The other thing I want to put in is I think you're getting close to retirement, John. So I'm not sure which date it is exactly, but thanks again for your contribution. Thanks again for putting this together for us and sharing your expertise and your experience. Wishing you the best in your new life challenges out there, and stay safe. Hopefully the border between our country will open soon.
That's right. That's right. Thank you very much. I appreciate it.
Thank you, guys. Thanks again for attending, and looking forward to another one. Thanks again. Have a good day.